Hi, hello, good evening, everyone. Myself, Avinash Rangaraju. I'm an assistant professor working at CMR College of Pharmacy. So today I want to discuss a very important naming reaction, which is usually what we call as Dakin reaction. So in this Dakin reaction, we were going to discuss what exactly this Dakin reaction is, followed by the general reaction and the mechanism of this Dakin reaction. Okay, so we'll start to proceed this Dakin reaction with Dakin reaction is nothing but replacement of aldehyde or acetyl group in phenolic aldehydes or ketones by a hydroxyl group in the presence of alkaline hydrogen peroxide. Okay, so if you look at the statement of Dakin reaction, it is mainly concerned with the replacement of aldehyde or acetyl group in phenolic aldehydes or ketones by a hydroxyl group in the presence of alkaline hydrogen peroxide, which means you're simply going to replace an aldehyde group or an acetyl group with a hydroxyl group. That is what we are going to do in this Dakin reaction. So if you want to see this basic reaction, the general reaction of this, so I'm drawing the structure of salicylaldehyde. So this is salicylaldehyde. This salicylaldehyde, it is having this aldehyde functional group, right? So this aldehyde functional group must be converted into hydroxyl group, that is OH, in the presence of alkaline hydrogen peroxide. So you're going to get a catechol ring system with two hydroxyl groups. Okay, so this is your hydroxyl group which you got by converting aldehyde into OH group in the presence of alkaline hydrogen peroxide. So if you look at this statement, you may have a lot of doubts in this. You may ask me how this aldehyde is converted into a hydroxyl group. So to understand this, we need to take up a reaction mechanism in detail. So I'm going to explain the mechanism of this Dakin reaction, okay, so that you will be clear with your doubts how this aldehyde group has been converted into an hydroxyl group. Okay, so coming to the mechanism of Dakin reaction. Okay. Now, Please listen carefully. I am going to explain this mechanism stepwise, so it will be very easy to understand. So I will proceed this Dakin reaction mechanism in 5 steps. Okay, so step number 1. That is formation of hydroperoxide ion. So initially, I'm going to react the hydrogen peroxide. You know, the formula of hydrogen peroxide is H2O2. So for better understanding of mechanism, I'm writing this hydrogen peroxide formula in this way: H, single bond, oxygen, another oxygen, and hydrogen. This I'm going to react with sodium hydroxide. Okay, so now listen. So this is your first step, formation of hydroperoxide ion. So initially what happens is the sodium hydroxide will undergo dissociation process to form Na plus and OH minus. Okay, similarly, you look at these two atoms here, oxygen and hydrogen. As oxygen is more electronegative, the electrons which are present in the sigma bond will migrate towards oxygen, where oxygen gets negative charge, hydrogen will get positive charge, right? Now, this positively charged hydrogen reacts with negatively charged OH minus to form a water molecule. This is how water is eliminated out as a byproduct. So you're remaining with hydrogen and 2 oxygen atoms. Okay, so this oxygen is having negative charge. That means it contains 3 lone pair of electrons. But actually oxygen will have only 2 lone pair of electrons. But when the bond is broken between oxygen and hydrogen, these electrons also migrate towards oxygen atom. Therefore, oxygen will get 3 lone pair of electrons. So this is your hydroperoxide ion, which you got in step number 1. Okay, so coming to step number 2. Step number 2 is nothing but addition of hydroperoxide ion to positively charged carbon. Okay, so see the statement here, what I have written in step 2. Addition of hydroperoxide ion to positively charged carbon. Already we have hydroperoxide ion generated in step number 1. Okay, so addition of hydroperoxide ion to positively charged carbon. That means first we have to generate a positively charged carbon, then hydroperoxide ion can be added towards this positively charged carbon. It is simply an addition reaction. Now we are going to take the salicylaldehyde here. So it is having the normal benzene ring and aldehyde group C, single bond, H, double bond, oxygen. And here you will be having OH group. So this is salicylaldehyde. Okay, so what we need to do is we have to generate a positive charged carbon. How can we generate a positive charge on this carbon? You listen. You compare the electronegativities between this carbon and oxygen. You know, oxygen is more electronegative. So it will pull these electrons towards this oxygen. So the electrons which are present in this pi bond will be migrated towards oxygen. So therefore, this carbon will get a positive charge. Now you can add this hydroperoxide ion. Okay. So you can add this hydroperoxide ion. So what is happening here? So already oxygen is having 3 lone pair of electrons, right? So what is the actual number of electrons should oxygen contain? Only 2. So it is having one extra lone pair of electron. So oxygen is very clever. It will donate this extra lone pair of electron to this carbon. Therefore, this carbon will form a new sigma bond with oxygen like this. I will show you in the structure. So you can draw the same benzene ring, okay, with OH group as usual. The same benzene ring I have drawn here. The same OH group I have written here. So what is a new thing I'm going to do is just I'm going to, so here you will get only single bond oxygen. Why? Because you have transferred this pi bond towards oxygen. So you are left over only with single bond. And here we'll be having hydrogen atom. Okay. And this is your hydroperoxide, and this is oxygen. Okay. Now this oxygen is having 3 lone pair of electrons. Now listen carefully. So what we have done in step number 2 is addition of hydroperoxide ion to positively charged carbon. So I have taken salicylaldehyde. So this is your aldehyde functional group. Okay. So you compare the electronegativities between this carbon and oxygen. As oxygen is having more electronegativity, this pi bond will be migrated towards oxygen. So the adjacent carbon will get positive charge. Okay. Now to stabilize this positive charge, I'm using this hydroperoxide ion, which you got in step number 1. So here what is happening, this hydroperoxide ion, right? Oxygen is having 3 lone pair of electrons. I will transfer 1 lone pair of electron to this positively charged carbon. So what happens? This entire hydroperoxide ion. Okay, so this is your hydroperoxide ion, right? The entire hydroperoxide ion is added for this carbon. So carbon has formed a new sigma bond. This is a new sigma bond which is formed between carbon and the hydroperoxide ion. Okay, and this oxygen is having 3 lone pair of electrons now. Why? Because as pi bond is shifted towards oxygen, originally oxygen will have only 2 lone pair of electrons. But when you shift this pi bond, oxygen will get 3 lone pair of electrons. Okay, so this is your step number 2. Okay, next, coming to step number 3. So step 3 is nothing but migration of phenyl group from carbon to adjacent oxygen with elimination of hydroxyl ion. Okay, now we will see how this step number 3 proceeds. Okay, so right. Now I'm going to write the reaction for step number 3 here. So I'm going to write the same product, what you got in step number 2 once again. Okay. And here you'll be getting oxygen will have 3 lone pair of electrons. And this is oxygen, OH, okay. And this is hydrogen. So right, this is your step number 3 product I'm writing, sorry, 2 product I'm writing here. So what is step number 3? Migration of phenyl group, right? This is your phenyl group from carbon. So this is a carbon which is directly attached with the phenyl group. So migration of the phenyl group from the carbon to adjacent oxygen with the elimination of hydroxyl ion. So first, I'm going to eliminate this hydroxyl ion. So when I break this bond between oxygen and OH, okay, this OH is a very good leaving group. It can leave the reaction with a negative charge. Okay, then what happens is this phenyl group from the carbon atom, it migrates towards oxygen. So when phenyl group migrates from carbon to adjacent oxygen, this carbon will get a positive charge. Okay, so to stabilize this positive charge, already oxygen is having 3 lone pair of electrons. I will transfer 1 lone pair of electron to this particular carbon. So therefore, carbon will form a double bond with oxygen. Okay, so here there is elimination of OH minus. Okay, and you can write the structure, the phenyl ring, the same OH I'm writing here, followed by, so as phenyl group is migrated towards oxygen, so here you can write oxygen, right, followed by carbon, hydrogen, and here you will be getting a double bond. Okay, because carbon is having positive charge here. To stabilize this carbon, oxygen is having 3 lone pair of electrons, but actual number of electrons on oxygen should be only 2 lone pair. So this extra lone pair of electron, oxygen will donate for this carbon. So this carbon will form a new bond. That means carbon will form a double bond with oxygen like this. Okay, so this is your step number 3. Coming to the next step, step number 4. So I'll try to erase this so I can accommodate the reaction for step number 4 here. Right. So again, I'm going to write the reaction here, step number 4. That is formation of formic acid is your step 4. And I'm going to write the product what you got in step number 3 once again here. Okay, so right. So it's very simple here. Now we need to understand how this formic acid is formed in 4th step. You compare the electronegativities between carbon and oxygen. You know, oxygen is more electronegative. So I will shift this pi bond towards oxygen. So what happens to this carbon now? Carbon will get positive charge. Now to stabilize this carbon, we require a very powerful nucleophile, negatively charged compound. So I will use OH minus here. Where from you are getting this OH minus? See, OH minus we have removed. in step number 3. So whatever the OH minus which was eliminated in step number 3, I'm taking the same OH minus or hydroxyl ion in 4th step to stabilize this positively charged carbon. Now this OH minus is going to attack this positively charged carbon. Okay, therefore what happens? This carbon will form a new bond with OH minus. Okay, so you can write here the benzene ring, oxygen, as one of the pi bond has migrated towards oxygen, you will get only single bond with oxygen, 3 lone pair of electrons, followed by hydrogen, and this is a new bond formation. Okay, of course, you'll be having one OH also here, the same OH I have written here. So this is a new OH which is formed. So this OH minus is going to attack the positively charged carbon. Therefore, carbon will form a new bond with the hydroxyl group. Okay, so in the next step, what happens is we are going to form a product called as formic acid. So I'm going to break the bond between this carbon and oxygen. It's very easy. So due to electronegativity difference, the electrons which are present in this bond will migrate towards oxygen. As oxygen is more electronegative, the electrons which are present in the sigma bond will migrate towards oxygen. Okay, so what happens to carbon here? Carbon will get positive charge. Okay, so this positively charged carbon can be stabilized by using this lone pair of electron on oxygen. Oxygen is having 3 lone pair of electrons. If oxygen donates 1 lone pair of electron for this positively charged carbon, so this carbon can form a double bond. Okay, so you can write the benzene ring or phenyl ring with oxygen. So it is having 3 lone pair of electrons and OH group here, plus you are going to get formic acid. So you can get C double bond O, H and OH. So this is formic acid. Okay, so this entire group is liberated in the form of formic acid. Okay, so in step number 5, that is the last step in Dakin reaction, that is formation of catechol and sodium formate. So the sodium formate is the byproduct, and this is your main product. Okay, catechol. So to write this reaction, I am going to erase this step number 3 here. Okay. So what is step number 5? Formation of catechol, that is a final product. So you can write the step number 4 once again here. Step number 4, final product, you can write here, that is oxygen. It is having 3 lone pair of electrons, OH group. And this I'm going to react with your formic acid. Okay, so this is your formic acid. So what happens is you compare the electronegativities between this oxygen and hydrogen. So generally oxygen will have negative charge, hydrogen will get positive charge, right? So hydrogen is least electronegative element or atom. So as hydrogen is having positive charge, you can stabilize this hydrogen by donating a lone pair of electron from oxygen. How many lone pair of electrons are present here? 3. But oxygen requires only 2. So this extra lone pair of electron, it will donate for hydrogen atom. Therefore, this oxygen will form a new bond with hydrogen atom to form OH. Okay, so you can write one product here, that is OH. Now oxygen will have only 2 lone pair of electrons, and this OH is coming from step number 1, which is common. So this is your catechol, the main product. And this is how we converted an aldehyde group in salicylaldehyde to OH, that is hydroxyl group, in the presence of alkaline hydrogen peroxide. Plus, you are going to get one byproduct also. What is a byproduct here? Sodium formate. So I'm going to use this sodium. Where from you're getting the sodium again? Don't be confused. If you remember this step number 1, okay, when we are reacting this hydrogen peroxide with sodium hydroxide, okay, the negatively charged OH minus has reacted with positively charged H plus, and we have removed water molecule there, but we have not reacted with sodium. So that sodium I'm going to use in step number 5, which is having positive charge. So this positively charged sodium reacts with negatively charged oxygen to form sodium formate like this, NaO minus C double bond O H. This is sodium formate. Okay, so this is catechol, which is a main product. Okay, and this is about your Dakin reaction. It's very, very simple. In Dakin reaction, we are going to convert a hydroxyl group of phenolic aldehyde or phenolic ketone into hydroxyl group in the presence of alkaline hydrogen peroxide. Okay, so it is a 5-step process. We need to understand the mechanism, how this aldehyde is converted into hydroxyl group, that is OH. Okay, so step number 1 is formation of hydroperoxide ion. Step number 2 is addition of hydroperoxide ion to positively charged carbon. Step number 3, migration of phenyl group from carbon to oxygen with elimination of OH minus. Step number 4 is formation of formic acid. Step number 5, formation of catechol and sodium formate as a byproduct. Okay, and if you ask me, sir, in what way we can use this Dakin reaction? What are the important applications of this Dakin reaction? So I can give you one important point. This Dakin reaction is very important in the preparation of polyhydric phenols from naturally occurring hydroxyaldehydes. Okay, so you can prepare some polyhydric phenols. Okay, so these polyhydric phenols are having very good antimicrobial properties. Okay, so this is what I want to discuss regarding this Dakin reaction. So in my next video, I'm going to upload few more important naming reactions which are extremely important for your application point of view in pharmacy, and at the same time for the examination point of view also. This type of mechanism will be very helpful and more simplified, because in most of the textbooks, you find the mechanisms little bit more complicated. So just I have simplified the mechanism in 5 important steps. Okay, you can follow my video, and it's end of this Dakin reaction. See you later. Bye bye.